So if we were to write a secret message, right, using only numbers and row matrices, we would have to begin with this key right here, where 0 is a space, and each number corresponds to each letter within the English alphabet. So, how can we create a message that conveys "Meet me Monday"? So, we're going to partition the matrix. We'll have to partition the message into groups of 3, such that it will produce the uncoded row matrices desired. So what does that look like? Well, we're going to need matrices of 3, and it's going to look something like this. Go ahead and pause the video and figure it out yourself. And while you're tinkering, I'm going to cut straight to the following matrices you should have. So these should be the partitioned matrices, and you'll see that each matrix has columns of 3. And if we were to decode it based on a given key, we would have the message like this: MEET underscore ME underscore MONDAY underscore. And there you have it. You now have a secret message telling you when to meet someone somewhere. Of course, this methodology has multiple applications, and right now we are starting off simple. So we know how to form uncoded row matrices. That's what we just did. Now what about when it comes to encoding a message? So let's say we're given this invertible matrix. How can we use this to encode the message "Meet me Monday"? Well, to encode a message, we have to choose an invertible matrix and multiply the uncoded row matrices to the matrix to obtain the coded row matrices. And what that looks like in practice is the following. So remember those partition matrices we had earlier to decode the message "Meet me Monday"? Well, we're using them again, and we're going to multiply them by the encoding matrix A. From this matrix multiplication, we are left with the coded row matrix. And that's how you're supposed to find the coded row matrix. Now let's go ahead and pause the video and work out the multiplication yourself. And while you guys are tinkering, I am going to cut to what your answers should look like for each operation. And here we have it. This is what your encoded row matrices should look like. So we now have the sequence of coded row matrices, and if we were to put them right next to each other and remove the matrix notation, that should produce a cryptogram. Now, what is a cryptogram exactly? Well, it's simply a message written according to a secret code. And a cryptogram is often deduced by using matrix multiplication to encode and decode messages. So what does that look like exactly now that we have our coded row matrices? Well, I'll show you guys. So here is the sequence of coded row matrices. Now what happens if we remove the matrix notation? What would that look like, and what would be the result of doing so? So we got our matrix notation removed, and what we have here as a result is a cryptogram. Now if we were to go back, the encoding matrix A, if we didn't have that matrix, this would be a lot harder for us to solve, and that's kind of the whole point. If there was an authorized receiver who knows the encoding matrix A, decoding would be a relatively easy process. The receiver would simply need to multiply the coded row matrices by the inverse to retrieve the uncoded row matrices. So that just means that if we have x, right, and it was equal to the following x1, x2, and how many terms there are, if that was an encoded 1 by n matrix where you can have as many columns as it wants, then the following equation, y equals xa, is the corresponding encoded matrix. As a result, the receiver of the encoded matrix can decode y by multiplying both terms by a to negative first power. As a result, we get y times a to negative first power equal to x. And that's pretty much the fundamental when it comes to encoding a message, as well as decoding one as well.